Hi, welcome. Thank you so much for joining my video on how we use symmetry with geometric figures. We're going to be talking about rotational symmetry and reflectional symmetry. So the first couple words that we're going to talk about are order and magnitude. Order and magnitude go with rotational symmetry. Order is the number of times a figure can be rotated about its center to map onto the same image. So, for example, if I had a rectangle like I have here, I would be able to rotate that rectangle twice, and both times 180 degrees and then 360, it would bring me back to that exact same image, the exact same way it looks, how it's longer this way, shorter like this. Okay, so I could rotate that rectangle once or twice and bring it back to my original, like this folder. So this is my main folder. I could rotate it 180 degrees and it looks the same. And then I can rotate it another 180 degrees and it looks the same. So order would be how many times I can rotate it so it looks identical to its original self. And so in this case, the order would be 2. I can rotate that figure twice to have it map on exactly to itself. The magnitude is the degree in which you can rotate it, which I already kind of mentioned before, but if you didn't realize it, when you rotate something halfway through, that's 180 degrees. Well, the magnitude here, if I rotate it, would be 180 because you do 360 divided by the order to get the magnitude. So the magnitude would be 180. Reflectional symmetry is about a line of symmetry down a figure in any form. It could be vertically, horizontally, diagonally, that when reflected, maps the figure onto itself. I always talk about my hands being like a reflection. If you could imagine a line down the center of my hands, that would be my line of symmetry because my hand perfectly reflects onto it. If I look at my own hand does not have reflectional symmetry because I can't put a line down the middle and have it reflect over perfectly. I can't put a line this way and have it perfectly reflect over. It would not be the same, okay? Now, this figure here, this rectangle, has line symmetry horizontally because I can cut a line through the figure and have the top fold over. Imagine that was a piece of paper. You could fold it in half that way and it would perfectly map onto itself, or I can fold it vertically. And if I fold it that way, it also maps onto itself. So this figure has 2 lines of symmetry. Now, the most common error that I get whenever I'm talking about symmetry with a rectangle is students think that the diagonal is also symmetry, but it's not. So if I did my 2 folds that I showed you before, lines of reflection, that would be one reflection line. Okay, if I fold it long ways, that would be my other reflection line because they map perfectly onto each other. But if I went diagonal to diagonal and I folded it from one point to the other, it doesn't map perfectly onto each other. These are congruent triangles to each other, yes, my diagonals, but it actually does not map perfectly onto it. So if I had this figure here and I folded it on my diagonal, it would not match up. So that's not going to be a line of symmetry. All right, so now we're going to look at the shapes that you see here on the side, and we're going to talk about the reflectional and rotational symmetry for each one. I have some figures here for us, but I want you to think about what you think the answer would be before I tell you. So our first figure is going to be a nice equilateral triangle. If I have this perfect equilateral triangle, think about how many times could I rotate it until it looks like itself. So if I keep my fingers here at the top, I can rotate it once, twice, and then a third time back. So my order for this equilateral triangle is 3. 360 divided by 3 gives me the magnitude, which is 120. Reflection lines. Think about how many lines of reflection do you think you could draw or fold this figure into? Okay, when figures are equilateral or regular, okay, it's always going to match up with how many sides or angles it has. So in this figure here, the amount of lines of symmetry I would be able to draw is 3. 1, 2, 3. Now, a square. My next figure, a square. If I keep my finger in this point here and I rotate it, I can rotate it once, twice, 3 times, and 4 times back. So my order here would be 4. 360 divided by 4 is 90 degrees, so it has a magnitude of 90, and reflection lines. So now reflection lines here, I can draw them through the centers from the sides. So here's what 2 lines of reflection would look like. But I also, for a square, can draw diagonal reflection lines. Only for a square, not like a rectangle, can we actually have those diagonals. So we could actually fold it along the diagonal, only a square, and have it perfectly match up. Now, a rectangle. A rectangle is what I talked about before. A rectangle is going to be able to be rotated twice, once, twice, back around, so the order is 2. The magnitude is then 180, and reflection lines. We talked about there's only 2 lines of reflections for a rectangle. It's the horizontal and the vertical. Now, a parallelogram. This figure here. If I rotate it once, it looks identical. If I rotate it twice, it looks identical. So my order is 2. My magnitude is 180. Reflection, though, is kind of tough because, look, if I go to reflect this over, let's say, the horizontal, notice the points don't match up. They wouldn't. If I folded it vertically, let's say, that's definitely not going to match up. Folding it diagonally, also, you'll notice the points don't actually match up. So there's actually no lines of reflection for this figure. Next one, Pentagon. So I can rotate it once, twice, 3 times, 4 times, or 5 times. So my order is 5. 360 divided by 5 is 72. Reflection lines. When it's a regular pentagon, I can draw 5 of these reflection lines. All from each vertex to the midpoint of the opposite side would be a line of symmetry. And these would be my 5 lines of reflection. This irregular pentagon. Okay, so this is a regular pentagon and this is an irregular pentagon. They both have 5 sides, but this has congruent angles and congruent sides. This does not. So here for this one, rotational symmetry. If I have this figure looking this way and it's pointing in this direction, if I rotate it 180 degrees, does it look identical to the way it looked before? No, it's pointing in the other direction. So I'd have to rotate this figure 360 degrees just to get it to be exactly the way it was. And if you have to rotate something 360 degrees, then it has no rotational order. Therefore, it has no magnitude. Now, reflection lines. Reflecting it vertically is not so great, but reflecting it horizontally. If I reflect this pentagon like this, that would be my 1 line of reflection. An isosceles trapezoid. So here we have this figure. Order. This is the same idea. If I was to rotate this 90, no. 180, no, does not look identical. It would have to take me 360 degrees to make it look the same. So my order is none and my magnitude is none. Reflection. If it's isosceles trapezoid, I'd be able to reflect it perfectly over the center line, the midpoint of the 2 bases, and I could have 1 line of reflection. A star. Okay, order, I have 1. So if I keep this point 1, 2, 3, 4, 5, right back. So my order is 5. 360 divided by 5 is 72. Now, lines of reflection. So lines of reflection, I would be able to draw from each point to its opposite side. And just like my regular pentagon, I would have 5 possible lines of reflection. And my last one, this figure here. This is an irregular dodecagon, excuse me. So looks like a giant plus sign. If I had the order, I'd have it 1, 2, 3, 4. Okay, so my order is 4. My magnitude is 90, and my reflection. I can draw a vertical reflection line. I can draw a horizontal reflection line. I can draw also a reflection line like this. And then one have 4 lines of symmetry. Okay, so now what I'm going to suggest that you do is you write down the alphabet, capital letters, A through Z, just like I have here. And on your own, give yourself a chance to figure out what you think the order is. Could you rotate that letter so it looks identical to itself? Figure out the magnitude if you can, and then how many lines of reflection would there be? A lot of these are going to have none of them, but a few of them do have a little bit of each one. So I would pause right now, give yourself a shot, and then join me back to see if you have it right. Ready? Go. Here is what the list should look like. You can see which ones have none, which ones have 1 line of reflection, or an order of 2. See how you did. Give it a good shot. If you didn't try it yet, maybe cover this back up, go back and give it a shot. I hope this video was helpful for you. Thank you so much.